Hi everybody. This is our lecture on section 4.6 on the rank of a matrix. Consider an R by C matrix A. Say that A has P pivot columns, right? Since a pivot has P pivots, a pivot takes up one row and one column, right? Each pivot accounts for a row and accounts for a column. Thus, A has P pivot columns, and so the dimension of the column space of A, like we've been discussing, is P, because it has a basis of P vectors. Okay, those pivot vectors. Okay? Since A has P pivots, as P pivot columns, also A has P pivot rows. Is there another vector space defined by A having dimension P aside from the column space of A? Well, the answer, of course, is yes, and that's as follows. So, for example, say that A is equal to the following matrix here, 3, 1, 4, 2, 0, 1, 5, 5, and 0, 0, 3, 2, and 0, 1, 8, 7. Okay, so we can reduce it to the following matrix. So now I'm going to subtract row 2 from row 3. 3, 1, 4, 2, 0, 1, 5, 5, 0, 0, 3, 2, and then 1 minus 1 is 0, 8 minus 5 is 3, 7 minus 5 is 2. So now we can reduce it a little bit further by subtracting row 3 from row 4, and that will give us a row of all zeros and reveal to us that A has 3 pivots. Get it all in on one row here. 3, 1, 4, 2, 0, 1, 5, 5, 0, 0, 3, 2, and then all zeros. All right, so this matrix has 1, 2, 3 pivots. All right, 3 pivots, 3 leading coefficients, whatever you wanna call these things, right? So now what vector spaces do we have now associated with A? Okay, well, the column space of A, so 3 pivots in columns, let's make sure we say which columns they are in, 1, 2, and 3. So the column space of A is the span of columns 1, 2, and 3 of the original matrix. 3, 0, 0, 0, 1, 1, 0, 1, and then 4, 5, 3, 8. 4, 5, 3, 8. And then that fourth column is dependent in some way on the first 3. one could try to figure it out, but it's not totally necessary to do so. Okay, we've already determined this. All right, so the column space of A, right, is the span of the three columns of A. And we learn that by finding out that A has pivots in columns 1, 2, and 3 by reducing to echelon form. But we also have three pivot rows. So let the row space, before we do that, consider now the rows of this matrix. Right, we've been talking about columns of A a lot, but now let's consider the rows of A. Of course, they're not vectors in the sense that we've normally talked about. Vectors in the sense that we've been normally talking about are essentially n r by 1 matrices. However many rows, one column. Okay, but I mean, there's no real reason to insist that they be, n by 1 matrices. They could be 1 by n matrices. Okay, so we consider n by, or 1 by n matrices as vectors as well as n by 1 matrices. Okay, so the four row vectors of A, where's my cursor? There it is. The four row vectors of A are right here. So we'll call them row 1, and that's this matrix. And then row 2s, 3, and 4. Let's spread these out a little. Oops. So that's row 1, row 2, and you can separate them with commas if you like. Row 3, and row 4. So these are the row vectors, and of course these are row vectors are transposes of the usual column vectors. Right? I mean, 3, 1, 4, 2, like that. When you transpose it is 3, 1, 4, 2. So that's the usual way of thinking about such vectors, but I mean, there's nothing inherently special about using columns as opposed to rows. Okay, so so we do that. So now let the row space of A, so that's row A, to be the subspace of R4, right? The subspace of R4 spanned by the row vectors, right? That is, linear combinations of the row vectors. Now, there's something a little bit different about the row space than about the column space, aside from just using row vectors rather than column vectors. Right? This is A, and this is A reduced to echelon form. The column space of this reduced matrix is not the column space of A. Okay, the basis of the column space, the reduced matrix, corresponds to the basis for the column space of the original matrix, but the vector spaces spanned are not the same. For example, there's always a zero in the fourth coordinate of the column space here. Not so here. I mean, obviously they're not the same. Okay, but you can pick out a basis here easily, and so you pick out a basis here easily for the column space. Now, the row space of the original matrix and the row space of the reduced matrix are the same. Why? Okay, let B be the matrix obtained from A by row reducing to echelon or reduced echelon form. Row echelon or reduced row echelon form, whatever the case might be. This is done with elementary row operations. And what are those elementary row operations? One, right, exchanging two rows. Right, so addition is commutative, so exchanging rows has no effect on doing linear combinations. If I exchange row 1 and row 2, and I do a linear combination of the rows, it's still a linear combination of the rows when you exchange them, because addition is commutative, it doesn't matter. Multiplying a row by a non-zero scalar. Well, multiplying by a scalar is something you do when taking linear combinations. You multiply a vector by a scalar. And you can divide vectors by a scalar by using the reciprocal of that scalar. Right, so number 2 is also something you do when taking linear combinations of row vectors. 1 is something you can do when taking linear combinations of row vectors. And 3, adding a multiple of one row to another row. Well, taking a row and adding a multiple of another row to it is a linear combination. Right? So, in short, okay, elementary row operations are just specialized linear combinations of the row vectors. So, right, if A row reduces to B, then the row space of A is equal to the row space of B. Right? Because you're just taking linear combinations of the row vectors of A. The linear combinations of the row vectors of A are what the row vectors of B are. They're linear combinations of the row vectors of A. So, I mean, it's just taking linear combinations in slightly different ways. Right? But they end up being the same subspace. The linear combinations add up to the same vectors. So whether you're doing linear combinations for A or linear combinations for B, it's fine. But with the matrix B, you know which rows are the pivot rows, so you can pick out a basis. So a basis for the row space of A are the pivot row vectors of B. Well, let's say. So a basis for the row space of A are the pivot row vectors of B, because those are clearly a basis for the row space of B. So that's a little different than with the column space. With the column space, you have to take column vectors of A, not column vectors of B. Here we take column vectors of B with the row space. So for example, in this example that we're doing, the row space of A, well, what's that original matrix? D, D, D. Let's make that a little smaller. The row space of this matrix is equal to the row space of the reduced matrix, which is this. Oops. All right, and a basis is given by the pivot rows of this matrix. So that's vector 3, 1, 4, 2. That's pivot row 1. And then pivot row 2, 0, 1, 5, 5. And pivot row 3, 0, 0, 3, 2. Alright, so that's 3 linearly independent vectors which span the row space of A, and of course this 0 vector doesn't add anything to the span. Okay? So that's the row space of A. So a little summary of a few properties here. If A is an R by C matrix with P pivots, then 1. The column space, the dimension of the column space of A is equal to P, and a basis for, well, let's see, let's add a little something else. No, just leave it like that. And a basis for column A are the pivot columns of A, not B, of A. 2, the dimension of the column space, or the row space of A. Well, let's do it this way. Hold on. If A is an R by C matrix with P pivots, and B is the matrix of obtained from A by reducing to row echelon form, then 1. The dimension of the column space of A is P, and the basis for column A are the pivot columns of A. The dimension of the row space of A is P, and a basis for the row space of A are the pivot. Whoops, why did I do that? The dimension of the row space of A is equal to P. The row space of A is equal to the row space of B, and a basis for row A are the pivot rows of B, not A, of B. 3, the dimension of the column space of A plus the dimension, so as we were saying before, of the null space of A is equal to C, the number of columns. Same thing for the row space. Dimension of the row space of A plus the dimension of the null space of A is C. But another difference is that the column space of A is a subspace of R to the R, number of rows. 6, the row space of A is a subspace of R to the C, with vectors transposed. Okay. So that is, that is just a little summary of these properties. And then finally, definition, the rank of a matrix A is just the number of pivots, right? Which is the same as, which equals the dimensions of the row space of A and the column space of A. Okay, so the rank of a matrix is just the number of pivots. So that's a more common term that is used other than pivots. So I don't know why they took so long to sort of get to that definition in the text. I would have presented it earlier, but there it is. So that's the rank of the matrix. It's just the number of pivots that you got. Couple other things just to round out the section. So given the terminology that we have developed in this chapter, we now have more ways of characterizing when an n by n matrix A is invertible. Right, so we did this way back in chapter 1. So let A be an n by n matrix. The following statements are all logically equivalent. They're all true or they're all false. 1. A inverse exists. Okay, so you have an inverse existing. And back in chapter 1, so let's go back to that characterization. That was in section 1.9, I believe. Let's take a quick look. Section 1.9. There it is. Or was it not here? It wasn't there. Where was it? 1.7? Oh, 2.3. 2.3, yeah, we didn't do inverse till chapter 2. Here it is. The following are satisfied. So an n by n matrix A has an inverse if and only if any of the following are satisfied, if and only if all of the following are satisfied. Same thing as saying they're all equivalent. A is row equivalent to the identity matrix. A has n pivot positions. Right? So that's the main one right there, number 2. A has n pivot positions. Okay? And then there was a lot of other ones here. The equation AX equals 0 has a unique solution, right? The columns are linearly independent. But now also we're going to have that the rows are linearly independent. So A inverse exists. So this is an extension of the theorem from section 2.3. So A inverse exists, and I'll write down the pivot thing. A has n pivots. The dimension of the column space of A is n. The dimension of the row space of A is n. The column vectors of A are linearly independent. The row vectors of A, because there's a pivot in every row, the dimension, because we have n pivots, the dimension of the null space of A is 0. Because the dimension of the null space plus the dimension of the row space is the number of columns, which is n. And that's enough characterizations. So this is in addition to the theorem from section 2.3. So all these different conditions for an n by n matrix tell you that you have an inverse. So if any one of these things is true, all of them are true. If any one of these things is false, all of them are false. Okay, so there's lots of ways to tell when a matrix has an inverse and when it doesn't. And we also had that one from section from chapter 3 about determinants. Well, let me add that one in there. The determinant of A is not 0, right? This was from section 3.2. All right, so determinant not 0, rows are linearly independent, columns are linearly independent, row space has dimension n, column space has dimension n, null space has dimension 0, all these different things, okay? All right, so that's the end of the lecture for this section.